So this is our fourth SolidCAM tutorial, and here's the part that we're working on in the other tutorials. So what I'm going to do first is just run a simulate just to see where we are in terms of machining the finished block. So I'm letting it quickly run through these simulations, and then I'm just going to switch the rest material on so we can have a look at what's still left to machine. And the big one at the moment is we've obviously got this excess stock around the outside of the part. So we're going to have a little look at that and a few strategies to get rid of it as well. So let's quit out of simulation. And I think the first operation type that we're going to try to get rid of that stock is just a profiling up. So if you remember from last time, we used a profiling up on this small groove around the top of the box, an O-ring groove, and this time we're going to use it to try and remove this excess stock. So just before we begin, if we look from above and view the part directly from above, you can see that the offsets that we put on our stock away from the finished part are quite small. Now if these were much larger, the profiling operation wouldn't be of much use to get rid of this stock. We're relying essentially on the fact that our cutter diameter that we're going to spec is going to be much bigger than this small difference between the finished part and the edge of the stock block, which you can see it's at its thickest at the corners here. Obviously along the flat faces the offset's something of the order of 2 mil. But obviously when it has to transition from this round section out to the corner, it's looking more like 6 mil. But our cutter that we're going to choose is going to be much bigger than that, probably 20 mil diameter. So we can essentially just send it around the outside of the part, just tracing around the outside, and just by the fact that it's so wide, it will get rid of all this stock as well. But as I say, if this stock block was a reasonable amount bigger, say 15 mil bigger than the part on all sides, we'd have to start thinking about other types of operation. The profile wouldn't be any good to us there. But with that said, let's add the profiling op in. So operations, add milling operation. It's going to be a profiling op. You may get this little notification. It's asking, it's telling us that tool 1 already exists. And do we want to import the tool with a new number? I think for whatever reason it's just ended up with a small conflict between the tool that it's trying to give us for this op and a tool that already exists. So I just clicked on OK, just said yes to that question. As it happens, the tool that we're going to use for this op, you can see I just flick down to the tool option there, isn't going to be the one that the system offers us. So if I go into select, I'm going to create a new tool by clicking down here, add milling tool. You can do this at any point. You can see a new tool has just popped up. It's given it the number 6 designation because we haven't used that yet in our operations. You can see this T1, T2, T2, T4, T5, T7. So it's given it the next free number, which is number 6. And we're just going to double click on that. Sorry, we're going to click on select. Let's try that again. There you go. We click the back arrow to come out of that dialog. So we've got tool 6 selected. We've checked that we're not currently using a tool 6, we're not, and we're going to modify the diameter of the cutting head here. We're going to spec a 20 mil diameter end mill. We'll just have a quick preview of what that looks like, and I think we're going to spec an end mill that's quite long, 150 mil long in total, and then we're going to bump up the shoulder and the cutting length to make sure that we have enough cutting depth there to engage with the size of our part. So you have to change the shoulder length first. You have to increase that in order to increase the cutting length. because obviously, as you can see from this graphic, the cut-in length CL sits within the shoulder length. So the shoulder length has got to be equal to, if not greater, than the cut-in length. And this graphic here is showing us these are the flutes of the part, and these provide the cutting edges to actually remove the material. So let's change the cutting length to slightly less than the shoulder length there, and you can see our little graphic here is updating to reflect these changes. If your cutter has a different arbor diameter, you can see the arbor diameter here. You can see in the graphic the arbor diameter is slightly less than the shoulder diameter. You can get that to be reflected on your 3D here by just dropping the arbor diameter down slightly. So I'll just drop it down by 1 mil, and you can see the transition there now. Sometimes that's useful to do just to give yourself an indication of where the shoulder length ends, even if it's not technically accurate for the cutter that you're using. But we're happy with that. Obviously you will have to source some relevant tool data here. We're going to look into methods of getting relevant cutting data for specific tools later on. But for the time being, that's where you need to be aware that you can enter the cutting data for the tool. So that's the RPM, the feed in X and Y, and the feed in Z, and any finish feeds that you may want to put in that are additional to the standard roughing feeds and speeds. So let's select that tool. We'll get some geometry for our operation now. So I've gone back to the geometry tab. I'm going to create some new geometry here, and I'm going to pick one of the edges around the bottom of the box here. So let's just pick this curve at this end. You can see it selected the curve, and as we said last time, auto constant Z is useful in this situation because it traces round the part on a constant Z level. We're using this coordinate system up here, not the default SolidWorks one down here. In SolidCAM and in most machining operations, the convention is to have Z as the vertical axis. So when it says auto constant Z, it's talking about the SolidCAM Z, not the SolidWorks default axes down here. So we've got that profile. We want to send our cutter around that profile. So let's set some levels that we want our cutters to cut at. We've already faced the top of this box. We've sent a facing cutter in down to this top face. So we're going to select that as our upper level, the top face. We've already got rid of all that excess stock above there. So that happens to be where our coordinate system was set, on the top face, so that's 0 level. Profile depth, we'll pick the underside of the box so that if the box was to change in depth at all, this value would be linked dynamically to the box itself. But rather than just let our cutter go to the full depth of the box, I think in this instance it might be useful to send it slightly deeper, so just so it clears this bottom surface of the box. And the reason I say that is the way that we've set up our stock block here is we've given a much greater offset on the bottom face here. You can see that illustrated by the pink wireframe here. And the reason I did that in the first place is that when you're designing these SolidCAM programs, another consideration that you must always have in mind is how is your workpiece or your stock block going to be held in place in the machine. And often the assumption is that the milling machine will have a vise bolted down onto the bed of the milling machine. And what you might do with small one-off parts like this is you might just push your stock block down into the vise and then clamp on two sides. So the thought here was that this pink stock block would be clamped here on this side by one of the jaws of the vise, and here on this side by the other jaw of the vise. and those jaws wouldn't extend upwards past this line, so past the bottom face of our finished part. So as you can see, if there's a vise sat underneath here and it's clamped on this section of stock material and this section of stock material, then when we are doing all our machining operations from above here, we can't go a significant amount past this bottom face. So we can't machine all the way down to the bottom of the stock block, because we would end up hitting the vice jaws with our cutter. But getting back to my comment about that I thought it would be useful if we went slightly beyond this bottom face, not a huge amount, maybe half a mil. The reason for that is when we've completed all the operations that we're going to perform on this stock block from this direction, so from looking at it from the direction that we're viewing it from now, what we're going to do is we're going to unclamp it from this vise, and then we're going to flip it over like that, clamp it down onto the machine again, either using soft jaws for the vise, or there are other methods that we could use to fix it in position. And then we're going to approach it from this side, so from 180 degrees, to put these counter bores in and to put this little engraved X letter in as well. And if you've come past the edge of this face on the first side, when we machine the first side, it just ensures that this edge here is neater. If you were to just select the profile depth so it was just as deep as this face, you run the risk of this edge becoming a poor finish. So it's good to go slightly beyond the depth of the finish face. And the way that we're going to do that, I've already clicked on that bottom face, and it's already given me a figure which is 30 mil away from the upper level. And that's good, because that's again linked to the part, and if the part was to change in depth, the SolidWorks part, SolidCAM would inform you that something's been changed, and it would update this depth figure. So say that changed to 29 or 31, this figure would auto update. So that's good. It's better than manually typing a figure in there. But we're saying we want to go just beyond that face, maybe by half a mil. And the way that you do that and keep that link back to the model is that you don't just type 30.5 in here, because that breaks the link. You type an extra figure in this delta box, and as you can see, as I click on that delta box, the graphic down here gives me a good indication of what I have to enter. It's basically indicating that if I put a positive value in there, it won't quite get to the 30. So say I was to put 0.5 in there, that depth would now be 29.5. So it doesn't quite get to the face that you've selected. But if I put minus 0.5, so just let me get the graphic back again. We'll delete that. So you can see there, minus indicates that the cutter will go slightly deeper. So minus for slightly deeper, plus for not quite as deep. So we want to go minus 0.5. So that will now take us down to 30, plus another 0.5 deep, so it will take us to 30.5. And we can test that when we run the simulation and the toolpath. We can check whether the cutter's gone just beyond the face or whether it's just above the face. So that's our levels taken care of. So at this point, it's often good to do a save and calculate and just see what the toolpath is looking like, even if you intend to go down and change some of the other tabs here, the technology and the link, for example. It's often good just to see what you've got so far with this operation. So I did a save and calculate there, and then I'm just going to put the toolpath on the model so I can view it. And we can see, if we spin the model round, we can see where the tool comes in. It's rapiding down to the finished level here. That's what the red line means. It's the machine's traveling in rapid traverse, which is essentially the upper limit of speed that the manufacturer puts on the table and the machining head. So it's coming down really quickly here, and then it's scribing an arc, and then presumably it's profiling the part. It's going around this profile shape, and then it's arcing back out again. So let's just have a little simulation of that. So I'm hitting simulate down here. I'm going to use Solid Verify in this case because it brings in the updated stock material with all the other machining ops already done on it. And then I'm going to just tentatively cycle through one step at a time just so I can check what's happening. So you can see the head's above the part currently, so I'll just go a couple of steps forward. It's dropping in now, so what it's useful to do on a new machining op as it's dropping into the part is just look from above and just check that it's not dropping directly onto any material there, because as we've said before, we're assuming this is an end mill, not a slot drill, and end mills can't really drill into the material as a traditional drill would do. You've got to drop down to a level and then enter into the material from the side. So that's good. So we've dropped down to the full level. We can check the level relative to the coordinate system here, and just as we thought, we're at minus 30.5. So if we look at the coordinate system, minus will always be away from the arrow, so we're down into the part, and we're 30.5, which is what we said, because this bottom face is 30 deep, and then we added that 0.5 on, just so that we go slightly beyond it. So we're still outside the part. We would expect to see the cutter arc in and start its profiling up now. So let's just go one step forward. It did a small move there, and there it is, just arcing into the to the part. And you can see the arc in there. That's just the end portion of it. So let's send the cutter around the outside. And again, if you imagine this cutter spinning clockwise, so we'll look from above. So this cutter's spinning in this direction and moving in this direction. So it's trying to roll its way around the part, which is what we said before. It's climb milling. So it's trying to climb its way around the outside of the part. That's what we said often gives you the best finish. In very specialist situations, you might send it in the opposite direction to the spin. So that would be, if it's spinning in a clockwise direction, then it would be travelling round in this direction. But 9 times out of 10 or 90% of the time, you're going to want to climb mill. So that's good that we are climb milling. So it took one pass round the part, and then it's arcing back out again. We can check that from above. Yep, it's cleared the part, and then it pulls up to its clearance level above the part. So let's just have a look. We'll just click play now just to finish that up. There's the finished up. Let's switch the rest material on, and you can see that it's finished the part on the actual finished surface of the geometry that we're trying to get to. So a few things to note about that. Number one is we can do the double check now and check that it has actually gone beyond the bottom face. You can see there that it has done. Number two is we're getting these little striation marks where the system seems to be telling us that there's some extra rest material there, but as we've said, the system resolves arcs and curves into a series of flats, so you've got to be aware that you often get these little phantom rest material areas on curves. But again, often it's nothing to worry about. It's just an artifact of the fact that it resolves a curve into lots of little flat sections. So that's okay. The other thing that we might want to note, if we just come out of there, is we did that in a single pass. Now that would be okay if the outside of this box, the finish and the accuracy of it didn't matter that much. And the reason I say that is when you take a cutter down and cut a depth such as this, so let's see how deep the box is. We already said it's 30mm deep. If you're taking a large amount of material off, the tendency is that the cutter might bend away from the material that it's cutting. So what that would mean in our case is the profile around the top of the box would be slightly smaller than the profile round the bottom of the box, because the fact that the cutter is pushing against the box and trying to cut some material away means the bottom center line of the cutter bends outwards slightly, because you're putting the cutter under a lot of stress. So if the finish and the accuracy of the box didn't matter, we could accept that operation and we could take all that material off in just a single path round the box. But let's say the finish does matter on that, so let's start putting some finish passes in there to take a small final cut. So you can see by default it's classed that entire profile as a finish pass, but we want to put one in before that, which is a roughing pass, and then we want to leave a small allowance of material on the roughing pass for the finish pass to come in and get rid of, because it's cutting a much smaller thickness of material away, the stresses on the cutter and the machine are a lot less, so you're going to get a much more accurate, much more finely finished surface. So I've given it an offset of 0.2 of a mil, and if we do a save and calculate there, so I put the roughing pass on, I'm going to leave step down at 0, and what that does is it means it ignores splitting this up into multiple steps and just does it in a single one. So 0 just means one step down, however deep the cut needs to be, just go down to the full depth and do it in one. So let's do a save and calculate again, and then let's zoom into our toolpath, and you can see that it's still got its original toolpath, which is this outer line, so it goes round the outside of the part, cutting the majority of the material away. But then when it's done that, it does a second pass, which is 0.2 further into the part, but on that pass it's only cutting 0.2 of a mil off all the faces, so the cutter will be under a lot less stress and you'll get a much better finish. So let's do a simulate of that as well. Again, we'll do a solid verify, and we'll turn the speed right down and hit play, so you can see it arcs in, takes the first pass and then takes the second pass. And again, the rest material showing that we've taken the material away and we're good. A few other things about this, if we just pop back into the simulation again and just play, you can see it goes down and then it pulls back up out of the part. Now that's quite wasteful. Obviously it's done its initial roughing pass there, but there's no reason for the cutting head to rise back up and then move back to its original position and then drop back down again. That's wasted time. So in all these operations, the ultimate goal is to make the operation as efficient as possible in terms of time, so the smallest time possible whilst still getting the tolerances and finishes and finished part that you require. So let's say that we want to get rid of that bit between the passes where it rises back up out of the part. Let's see if we can find an option in here that will allow us to change that. Links between passes, here we go. So we assume it's going up to the clearance level between each pass. So let's change this, keep tool down, and then we'll do a recalculate. So you can see that that little link between these two paths where it was transitioning over has now disappeared. So let's check that in simulation. I think we'll do it in step-by-step mode so that we're not going to run past where we need to be. So it's coming in for the first pass, it's taking that roughing cut, and then it moves slightly away from its arc. You can see it's still down there, so we've got rid of that motion where it rose up out of the part back to the clearance level. We've got rid of it. So if we're making a number of these, that saving in terms of time might be quite significant. There are other tweaks that we can make to this as well, and this is essentially what you'll be expected to do with your SolidCAM programs. Refine them, maybe keep a record of how you started and what refinements you put in and how much time that has saved, or why you changed, say, a tool type or a speed or feed. It's just evidence of how you've improved your overall SolidCAM program. So we're coming in for the first pass. And I don't know whether you could see that there, but there's a slight movement just inwards there between passes, and it may be possible to get rid of that. I believe that that relates to this lead-in of 0.25. So let's try changing that to 0, see what that does, and you can see that that little extra extension there was deleted. So it's all about getting into the technology tabs and the link tabs and trying different options to change your toolpath. But if you always have the toolpath visible in the main window there, you can see instantly what your modifications are doing. So you can see there that what I'm changing there is that distance that it moves away from the arc between passes. So in this instance I can drop that down to 0. Now the thing to note about modifying all these is these are specific to this instance. In some instances there might be material in the way, and coming out to the clearance level to move back to the start point is a good idea. But in our instance there's no rest material in the way, the cutter's not going to hit anything, so it's good to keep the cutter down, and it's good to get rid of that little extension line there as well. So you always have to be aware that the system tends to default into a very safe mode, a mode where even if there is material around the cutter that it shouldn't hit, it won't, and that's why it always comes back out to clearance level. It always defaults to the safest way of cutting the part, but that's not always the fastest way. So let's say that we're happy with that now. We'll just do one final simulation. Yep, we're good there. Put the rest material on, and let's look at what else we're going to tackle here. So I think the next thing that we'll have a look at are the chamfers on the top edge of this island, and the other one is around the outside of the box. So you can see there that there's some rest material that represents a chamfer that we're going to have a little look at. So we're going to have a look at the chamfer op next to create this chamfer around the outside of the part. And how we're going to start that is we're going to take a copy of our contouring operation, our profiling operation, sorry, that we took the stock away with. So I've got that selected here. If I just go right click, copy, and then right click again and paste, and what that does is it gives me a copy of that op with all the same details selected in there, and I'm going to go in and edit that. So the reason I did that is I want to reuse this contour data, this geometry that I used from that particular operation, but I want to change it to a chamfering operation rather than a operation to remove all the stock material from the outside. So one of the first things I'm going to do is change the tool type. So I've clicked on tool, select, I'm going to create a new tool type down here, add milling tool, and I want a chamfer mill, which as you can see from the graphic it looks quite similar to a drill, but it's able to cut whilst travelling in X and Y, so on the side of this angled face at the bottom, and it's for adding chamfers to the edges of things. It's defaulted to 10mm diameter. I'm happy with that. I can have a quick look at what that tool looks like, and that's fine for me. That looks okay. So again, you'd have to pick a relevant tool, an existing tool, from a tool supplier or tool manufacturer, find the tool data, the cutting data, given the grade of aluminium or steel or whatever metal you're using, and you'd have to input relevant RPM and feed data in these data boxes as well. So let's select that tool. Let's go down to levels. The upper level again is still going to be the top of the part. The profile depth, we're now going to select the depth of the chamfer. So if we zoom in a bit, we can select this bottom edge of the chamfer, and we can see that that chamfer is a 0.5 depth chamfer. We don't need that delta adjustment anymore. We can put 0 back in that box. And then at that point, I think we'll do a save and calculate and see what the path is looking like. So save and calculate, and then view the path. So you can see that we have that roughing pass and finish pass from the last operation. I don't think we need both of those. I think we're going to create this chamfer in one pass. So if we turn the roughing pass off and do a recalculate, you can see that it's now taking all that material off in one pass. The reason I've done that is the quantity of material that's been removed here is nowhere near as large as the amount that we were taking off when we were machining these faces around the outside. So the tool's under relatively low amounts of stress, so you should get a fairly accurate finish just doing it in a single pass. So let's look at how it enters and leaves the part, and we'll do that in simulation. So solid verify. You can see that now that material's been removed from the last operation there around the outside of the part. When we'll do a step mode, so we start off above the part. If we look from above, we're actually outside of the part boundary as well. The head drops down. It drops down to about there, and then if we view it from above, I think what we'll see is it will arc into the job, so it will swing from here into the job through 90 degrees, and there it goes. So it swung through that arc. It should now be at depth 0.5, yes, and then initially we're not getting any material removed. And the reason for that is that what it's done is it's taken the full diameter of this chamfer tool, so this outer cylindrical surface here, and it's pushed it up against this outer profile that we've selected, this shape. And the reason that that doesn't cut anything is that the tool tapers towards its end, so there's actually no contact between the tool and the part at all. But if you were to look at it sort of square on from this side, let's see if we can find the icon to do that. There we go. You can see that technically this vertical face is in line with this face. So it's treating it as a normal milling cutter, and that's not what it is. It's a chamfer tool. So we need to add some more data in there to tell it that it's cutting on this 45-degree angle surface, not on this vertical cylindrical surface. So let's come out of simulation and see if we can find the option that does that. And where it's located is in this option here, this rest material stroke chamfer. And if we select chamfer in there, we get a whole new menu here, a whole new tab. And the first thing that we're confronted with is this cutting diameter. So if we click on that, we get a nice little graphic explaining what that means. And as you can see, if this is our finished chamfer, we don't cut right on the tip of the part or the tip of the tool. We actually specify a small diameter there, which will hit the bottom edge of the chamfer. So this is a good idea normally, because these chamfer tools they tend to be more worn near the tip than further up the face. So if for no other reason than that, it's good to specify this cutting diameter as a reasonable amount up the face. So I've put 3, maybe 4 might be more useful to us. And then if we do a save and calculate now and drop back into simulate, let's go into solid verify. The tool should trace out a similar path, but it should now be closer into the part. So let's try and line the part up so that we can see the tool entering that one. So let's see as it arcs in whether it makes contact. There, it seems to have just entered the part there, you can see. And then if we advance one more step, yes, it's cut some material away. So if we go around to the opposite view, so now we're looking at it as it travels along that edge away from us. If we zoom right in, you can see that it's taking a cut out of the edge of the part there. And we can assume that this diameter across the cutting tool here is our 4mm. So that's what the 4mm cutting diameter does, and you can see it's removed the material there. So that's good. So it's travelling around the part using our profile and using that cutting diameter, and then when it gets to the end it should arc back out again. There we go. So it arced back out, so it was clear of the part, and then that's our finished cut. If we put rest material on afterwards, we can check that it's got all the material. Again, we're getting these slight artifacts on the curves here, nothing too much to worry about. It's just that it's flattening out those curves into a series of straight lines, that's all. So we're reasonably happy with that. One further thing to consider though is that when you're creating a chamfer round a loop of edges, which is what we've done, where the chamfer tool returns to the start point again, if you arc inwards like this and then start the cut, and then similarly once you've finished the cut you arc outwards like this, what you tend to get is you are able to see that transition from the head running round the chamfer shape to it arcing in from outside the part and arcing back out again. So these the method that the tool enters the part here, I think we would be wise to try and change that to something that's going to leave less of a witness line, because that's what you tend to get. There's a little witness line to indicate where the tool entered the chamfer and where it exited the chamfer. So there are better ways of sending the tool into the job and then bringing the tool back out again. And we would access that through the link option, and it's this lead in and lead out that we're interested in. So the lead in, I would say we'd be better off entering the job on this arc here and entering it so that we were tangent to that arc. So let's see if we can make the cutter do that. If we open up this lead in option, you can see that we have the arc selected currently, so we're coming round at a 90-degree arc there and coming into the job. As we've said, a tangent option might be better, so if we just change it to tangent and then do a save and calculate, you can see what's happened. You can see at the moment we have this lead out option set the same as the lead in option, so they've both flattened out, and this exit one is now pretty good, because what it's going to do is it's going to run along this straight edge at the end of the cut, and then it's just going to keep going out of the part and then raise upwards. So I think we've improved the lead out, but the lead in, it's dropping straight down onto this edge and then starting its way around the part. What we could do with doing is shifting both of these round onto this arc portion, because they're entering and exiting based on this straight portion of the geometry. We want them on this arc here. So let's see if we can do that. If we go back into technology and then click the technology tab, and we want to play around with the geometry that we've entered in the first tab, the geometry tab. But the way that we play around with it and change the start point and such is that we go into technology, hit geometry, and then we get a preview of what the system considers the start point of our geometry. So you can see here's a representation of the cutter. This is the outside diameter of the cutter. It's showing us the direction that the cutter is going to travel off in, but we want to shift this start and end point round onto this arc slightly. So let's have a look at the start position dialog here, and let's just move it around something small. Let's say 1%. So if you enter 1 there and then just click out of that box, you can see that the update actually changes, and that's pretty much ideal for us. That's sort of halfway along that arc. So let's OK that and do a save and calculate, and you can see what's happening now. We'll actually do a simulate, but before we do, you can see that the tool starts here, it rapids down until it gets to the green line here, then it slows down and enters the part in a controlled manner. So it would enter the part at 300 millimeters a minute, because that's feeding Z that we've set for that tool. So it enters the part quite slowly here, and then it traces a straight line here onto this arc, and then starts off round the part, comes all the way back, comes to the end of this straight, starts to go around that arc again, and then just exits by tracing a straight line. And if we want to exaggerate that, we can go back into link, maybe put a bigger value in the length here. You can see that we've exaggerated what's happening there now. So it's entering from and exiting from a much greater distance. So we'll have a look at that. So let's simulate that again. We can watch that actually happening. So you can see that we're at the end of that line, that entry line. Enters onto the part, hits that curve, tangent. It's whizzing round the part now. It's coming back to the start point again. You can see that there's still a little bit here to cut to join these two cuts up. It should go part way around the arc and then exit tangent on a straight line. So that's quite good. That's going to produce a reasonable finish there. There'll still be a slight witness line between where it started and where it ended, and let's see if we can play around with that now. So what it would be nice to do is to have a slight overlap between where the cutter enters the part and where it exits the part, just to ensure that there's no little burrs or anything. It would be nice to send the cutter over this little portion twice, just to make sure that it's as smooth as possible. And the way that we do that in this particular instance is our tangent operation that is already entering via this 20mm line and exiting via this 20mm line. We want to put a little bit of extension on that, so let's put maybe 5mm of extension. Sorry, we'll not put that in the lead-in portion there, so let's put that back to 0. We'll actually enter that back in the Technologies tab in the Finish Pass option here. So you can see that it's defaulted to a small extension currently, but if we bump that up, let's put 5 in there, and let's go a little bit smaller actually, let's go 3mm, and just watch these lead out lines and lead in lines. So you can see there that there's now an angle between them, and what that means is as it comes into the job here, it enters this arc somewhere around this point here, and then it whizzes round the part, and then when it gets back to this curve, it comes round to about here before it starts to exit. So you can see that there's a portion in between those 2 points where it's going to overlap, and hopefully that'll give it the best chance of having a very smooth finish on that edge. So I think we're reasonably happy there with the chamfer operation. We'll just check it one last time. Dropping into the part, we're going into that arc shape tangent to it. We can zoom in and see how gradual that entry is. You can see that it gradually enters the cut there. That's quite nice. It goes off around the part, and then it comes back to join up and then overlap on this this curve. It goes past the entry point, so you get the overlap there, and then it exits on the straight line again. So that's reasonably good in terms of the finish. I think all we'll do is, there's no need to have these large extensions. We're just going to shrink those down a little bit, maybe turn them down to 10. But that's one of the things that you could play around with to try and get the time of this operation and the total time for all the operations down slightly when you're trying to optimize your program. Again, as we said before, it's often good to start naming your operations. The default names tell you the operation type that you've created, but it's not very descriptive. So let's call this one chamfer, or outside chamfer. Let's right click on it and rename. Outside, maybe chamf, just to keep them quite short. It retains the little notation at the end telling you which tool is being used, which is quite useful. And again, if we want to change this to outside stock, maybe that's a little bit more descriptive. You can right click and rename like I just did, or you can go in and while you're editing it you can change the operation name in there as well. So let's say outside stock, and do a save again, and you can see it just updates there. So it might be good as you build up your programs to name all the operations so that it's more obvious what each one does. So let's use the chamfer operation again. Let's tackle this little inside face here. I think for this one we'll start a fresh operation. We're not really going to use much from this operation that we just created other than the tool maybe. But let's create a new one. So milling, profile, we need to we'll go quickly through this one because we've done most of the steps here already for this previous. So let's quickly get some geometry, get the outside here, arrows in the right direction, yes, tool, we already have a tool. Let's pick the chamfer tool from last time. Levels, upper level, there. Profile depth, that edge. Technology, we need to chamfer this. Let's cut it at 4mm again to begin with. And let's stick with the arc just for the time being. Do a save and calculate, and then look at the toolpath. So let's have a little look at this toolpath. Now this might be one of the toolpaths where it could be quite wise to return back up to the clearance level between any passes that we're going to make, and that's because it's down inside a pocket that we're not allowed to cut away any of these walls. In this instance, because this upstand portion here is away from any of the walls, there's no chance that our tool would hit any of these walls. But if this was in a tight little corner and we were trying to move between the start and end points between passes, it may not be a good idea to keep the tool down. But let's have a little look at the simulate option for this. So we're dropping in, arcing in there, whizzing round the part, we're climb milling again, which is good, and then arcing back out again. And let's have a look at the rest material. So you can see that we've cut the part, the rest material's all gone there. Let's say we're reasonably happy with that. Let's check some of the options in there. Let's say we're reasonably happy with that and we can exit. So I think really the only thing that we've got left on this side of the part to finish off is this small pocket in the bottom of this feature. So let's create a new pocketing up. So pocket in. Again, we're getting this tool warning. If you just say yes to that, we need some geometry for this. So I'm going to just pick one of these edges and then auto constant Z again. It's defaulted me to a 10mm diameter tool. One thing that it might be useful to check here is some of the part geometry. If we look at the radius of curvature of these corners, so it's got a radius of 2, that one. Let's have a look at this one. Hopefully they'll all have the same radius. That one has 2 as well. I'm going to assume that they're all 2mm radii. So if you're trying to cut that with a 10mm diameter tool, that's not going to work, because obviously the maximum diameter of tool that you can get into this little tight corner here is 4mm. If it's 2mm radius, then it's a 4mm diameter tool. So I think what we'll do is we'll create a new tool. We'll have an end mill, although technically we will be using a slot drill here, but it's represented as an end mill by the system. And let's put a 4mm diameter on this. Let's just have a quick look at the tool. Let's say we're happy with all that. Again, speeds and feeds, RPM and feeding X and Y critical. You need to find this data from tool manufacturers. Their websites are often quite good, and again the Sandvik website is very good for getting this sort of data and evidencing that you're aware that this tool exists, you can buy this tool from somewhere, and that the manufacturer has some recommended speeds and feeds for you. So let's assume that we've entered all that data, and we'll start setting the levels. Clearance level for this, the Y's level to set the clearance level at would be above this top face, so that any big movements that the tool has to do, it comes out beyond this top face of the part. Just in case it decides it wants to move the tool off in one direction, it's not going to cut through one of these outer walls. But by default, it's set the clearance level to the part default clearance level, which is 25mm above the top face of the part. So we're happy with that. Upper level for this op is this top surface, because that's where the rest material that's filling this pocket begins. It begins in line with that top surface. Pocket depth will be down in the bottom of the pocket there. That's how deep we want to go. That's the maximum depth of it. And we have that's actually 2mm deep. That's what the pocket depth is telling us. It doesn't say -2 because in this box it doesn't really care whether it's positive or negative. It has a record that it's negative, but it's telling us it just happens to be 2mm away from the upper level. So we could do this in equal step downs. Let's change the step down to half of that, so it does it in 2 passes, and then do a save and calculate. And then show the toolpath there. So I think if we have a look at this toolpath, you can see that it's starting off 25mm above the coordinate system, or 25mm above the top face. It's rapiding down into the part, and then it's starting its helical path down into this pocket, and then it's I think it's spiraling out from the center, so you can see that these initial cuts are in quite a small trench, and then it jumps out here to the outside finished size and then whizzes round again. But let's have a little look at the simulation just to check that we are right in the way that we've interpreted that toolpath. So we'll go step by step. It's rapid into the job now, and again for our machine rapid is set at this high number here, so that's quite quick. When it gets close to the pocket, that reduces right down to our feeding Z that we've set for the tool. And then we may not see it spiral into the job here, because the spiral, there you go, it's done one spiral round. And the reason it does that is it's just kinda on the tool. If we were using a slot drill, we could drop straight into the material, but it's not kind on the tool or the spindle. Really, you should move them in X and Y as you're dropping them into material in Z. So it achieves this by just spiraling round a small circular pocket. And then you can see that it's created an offset of the edges of the outside of the pocket, and it's spiraling out towards them. Or rather, it's cutting a pathway in line with them and then stepping out slightly. And now it's spiraling in for the second cut. It's just dropping in Z now. Now it's spiraling in. You can see it cutting the circular pocket there, and then it's going to open that pocket out and then step outwards. Now that's interesting. Again, the tool manufacturer will have recommendations about this. This amount that it cut this inner pocket, and then it stepped outwards there. You can see the outline of the cutter as it stepped out and then moved along this section here. So that step over from there to there is available to us to change. So let's have a look in technology. And here we go. Minimum overlap between passes is a percentage of the tool diameter, 65%. So let's see how that affects our tool paths when we change that. So let's say rather than 65, that's quite a high step over, let's drop it right down and be very kind to the tool but very slow on this operation. So let's drop that down to 20. Let's bump that back up again. So this is the overlap between passes. So what actually happens is, as you increase this value, each pass you can see there becomes more similar to the last pass. So there's an overlap of the cutter of 90% now, which means that each of these passes is very close to each other. There's a big overlap between where the cutter was last time and where it is on the next pass. So we're doing it in multiple passes now. Now that's very kind to the cutter. It's not putting the cutter, this little 4mm cutter, under much horizontal load, so the cutter won't bend or deform, but it is slowing our operation down. So let's just have a look. So we set this at 90mm overlap between passes, and let's try and get an indication of how this affects the time for that operation. So let's just run this through. You can see it's dropping in, it's spiraling in, it's doing multiple passes now, maybe 5 or 6 different passes. It's spiraling in again, doing multiple passes down at the lower level. So it's finished, and we had a time of 1 minute 27. So let's change that value back to 65. You can see that the number of passes is now just 2. Let's run through again. So you can see that we've saved almost half a minute there. But the question is, would a cutter of 4mm diameter with a 1mm step down on each step handle that amount of that step out on each pass? So you'll have to source all that data from the cutter manufacturers. They have recommendations about percentage overlaps, or you can just put a millimeter value in here if you want. So that's essentially saying the distance between this first pass here and this pass here is 2.6mm. So if I was to drop that right down, let's put it at 0.5mm. you can see how that changes. If I was to bump it right up to 10mm, overlap is not in range because we've gone beyond the cutter size. 3mm, let's say. You can see that it increases. Let's go right up to just underneath the cutter diameter, and you can see the amount of passes there. Now what that's doing is, because the cutter diameter is 4mm, I've set this at 3.9, that it means the distance between each one of these is 0.1 of a mil. So that's how that value works. So if we drop that down to say 2 again, then it can do it in a single pass. So yeah, these sorts of figures, you need to get them from the cutting manufacturer, and they're obviously linked to the step down that we do. So we took this pocket in 2 step downs, each one cut in 1mm depth of material, and again, if we were to increase that to 2mm, so it could take the whole pocket in one go, then you'd obviously have to link this in with the overlap in here. So you might be able to get it all in one depth cut, but your step overs would have to be more gentle on the cutter. The only other things to consider here is whether you'd like this pocket with a very good finely tolerance finish on the walls and on the floor, and as we've said before, you can set all these options in here. Currently we're not actually getting out to the quite to the walls or to the floor. We've got this 0.3 offset on the walls and a 0.15 on the floor. We could drop these down to 0 and just cut it in one go, or we could put a finish pass in for the walls and a finish pass in for the floor. So if I do a save and calculate now, you can see those small finish passes in there, just finishing off the final cuts. But let's say we didn't need either one of those. We could just drop these down to 0 and it would cut to the final size. Let's just check in Solid Verify that that gets rid of all the rest material, and yes, we have. So I think we've pretty much come to the end of all the operations that we can do from this side of the part. What we need to be thinking about now is, as I said earlier, turning this part over in the milling machine, somehow clamping this down, maybe creating a new coordinate system to reference this second side, and then we need to be thinking about cutting these features on the other side. So these counterbored and drilled holes, this engraved X here as well, and I believe we might have a chamfer on that top edge also, so we have to consider that as well. But we'll have a look at that in the next tutorial.